So in this video we're going to have a look at how to answer all the questions in homework 4.1b, standing waves. So we start out with some warm-up questions, just explaining first of all how standing waves form. So first sentence, standing waves form when two waves of equal amplitude or frequency and wavelengths travel in the same or opposite directions and superpose. So to form a standing wave, those waves need to have equal frequencies and wavelengths. They must be travelling in opposite directions. And then the effect of the standing wave is formed by those waves undergoing superposition. And then we need to be able to explain why we get nodes and why we get antinodes. So in areas where the waves combine in phase or in antiphase, two waves combine destructively. So if it's destructive, the waves going in one direction must combine in antiphase with the waves going in the other direction, in which case we're going to get nodes. Remember, antiphase, destructive interference, node displacement. So nodes, node displacement. And then conversely, in areas where the waves combine this time in phase, the two waves combine constructively, forming areas of the greatest displacement, which we call antinodes. So, antinodes. For question B, we've got a picture of a standing wave on a string, and we're asked to mark in various different positions. So first of all, mark in nodes and antinodes. So the antinodes, relatively straightforward. They're these bits with maximum displacement. And in between those and at either end for a string, we have nodes. So fill those up there. We're told the string is of the length 0.8 meters, and then we want to find the wavelength. Well, if we have a look here, what we've got here is one wavelength there and another wavelength there. So that's two waves, and two waves are 0.8 meters. Then that means that one wave is 0.4 meters. So lambda is 0.8 divided by 2, so 0.4 meters. If we know the wavelength, we can work out the wave speed. If we know the frequency of the oscillation, we're told the frequency of the oscillation in B part 3 is 1000 Hertz. So we're going to go back to this most important equation in waves, V equals F lambda, and then plug in our numbers. So 1000 times 0.4 gives us simply 400 meters per second. And then the final part of this question, we're asked to relate this wave speed to the tension in the string and the mass per unit length. So we've got this equation here that wave speed is equal to the square root of tension over mass per unit length. So it's just a case of rearranging, sticking in our values. So if we square both sides of the equation to get rid of that awkward square root, v squared equals t over mu. And then we are told that 1 meter of string has a mass of 10 grams. We need to get that into the right units, which is kilograms. So 10 grams is equal to 10 times 10 to the minus 3 kilograms. So it's 10 1,000ths of a kilogram. Right, we've got everything in the right units. It's then just a matter of plugging into our equation. So we've got t is equal to 400 squared, so that's our v squared, times by mu, 10 times 10 to the minus 3. And we get 1600 newtons. For question C, we're asked to complete the diagrams for the open pipe, closed pipe and stringed instruments for the first overtone and second overtone. So that's the second and third harmonics. We've already been given the diagrams for the first harmonic, or the fundamental frequency, and it's quite useful to mark in what we've got at either end, because that will set the guidelines for the rules for each of these instruments. So for strings, we always have to have a node at each end. For an open pipe instrument, we always need an antinode at each end. For a closed pipe instrument, there's a node at the closed end, antinode at the open end. And we can then use those rules to build the rest of these diagrams. So in order for the second harmonic of the open pipe, we're still going to need an antinode at each end. And then the easiest way to get an antinode at each end, previously we had ANA, is going to be ANA, so Anna goes to Anana. And then similarly, antinode at each end for my open pipe for the third harmonic, and then I can mark in ananana. Sounds stupid, but it helps you remember, and certainly writing down these letters will really help you with your diagrams. So we can go through the same with the closed pipe. We have to have a node at our closed end, we have to have an antinode at our open end, and so we go from na to nana to nanana. And with a stringed instrument, we're always going to have nodes at each end. Those points are going to be fixed, so they're going to experience zero displacement. So node at each end, and whereas previously we had nan, here we're going to have nanan and nananan for the third harmonic. And then it's just a matter of drawing these in. So when you're drawing these, you've got to remember to have a solid line and a dashed line to show that it's a standing wave. I'm going to do it with red and blue lines. So I'm going to have an antinode like that, and something like that. It's a pretty rubbish diagram, but you get the gist of it. And then similarly, I've got an antinode there, antinode there, antinode there, and down like that, and something like that. So that's my open pipe instruments. For my closed pipe instruments, I'm going to start at a node. I'm going to have an antinode there and go down. Start on my node, antinode there and up. And likewise for the next harmonic, so it looks something like that. And then for my stringed instrument, something that looks like that, and something that looks like this. The next question asks us to mark in the wavelengths in the pipes for the and string for the fundamental frequency, and we're told the length of the pipes and strings in all cases is 1 meter. So we have to work out how much of a wave I've got. Here I've got half a wave, so if half a wave is 1 meter, my wavelength is going to be 2 meters. For the closed pipe, that's a quarter of a wave, right? The distance between node and antinode is a quarter of a wave, so if that's 1 meter, the wavelength is going to be 4 meters. And then here I've got a wavelength of 2 meters again with the string. Looking down with the open pipe instrument, whereas I've got this half wavelength once, now I've got half a wavelength once and then twice. So if you like, what I can even do is kind of split this into half. So if you like, what I've got is where I've got this pattern once, I've got it twice. So where my wavelength was 2 meters, it's now 1 meters, and I can work out what's happened to my frequency. If I have half my wavelength, because the wave speed is fixed, I must double my frequency. So frequency goes from 170 to 340 hertz. Similarly, what I could do is I could have that pattern 3 times for my next harmonic. So we can see we've got this kind of cross pattern that we've got there, once, twice, 3 times, and so my wavelength is now 1/3 length. I've got the same pattern in the same space but 3 times over. So that means that my wavelength is now 1/3 of 2 meters, so 0.67 meters, and my frequency is 3 times greater than 170 hertz, so 510. Here I can do the same thing. I've got a quarter of a wavelength once, a quarter of a wavelength twice, a quarter of a wavelength 3 times. So that means my wavelength, because I'm fitting that in the same space, my wavelength is 3 times greater. Sorry, 3 times less. So whereas it was 4 meters, it's now 4 meters divided by 3, so 1.33 meters. If my wavelength's got 3 times smaller, that means my frequency's got 3 times bigger, so 85 times 3 gives me 255 hertz. And again, how many quarter wavelengths have I got for my next harmonic? There's 1, 2, 3, 4, so 5 quarter wavelengths for my next harmonic. That means that my wavelength has got 5 times smaller. I'm fitting the same pattern in 5 times. And so 4 divided by 5 is 0.8 meters. If it's 5 times shorter wavelength, it's going to be 5 times greater frequency, so 85 times 5 is 425 hertz. And then the same thing again here with the stringed instruments. Here at the top I've got 1 loop, here I've got 2 loops in the same space, so the wavelength must have got half the size, so 2 meters goes to 1 meter, the frequency must double to 200 hertz. And again, where I've got 1 loop at the top, I've now got 3 loops at the bottom, so my wavelength must be 3 times smaller, so 1/3 of 2 meters is 0.67, the frequency is 3 times greater, 300 hertz. So that's the warm-up questions done. We'll go on to the main questions in a second. For question 1, we're asked to explain which of the following statements is not true about standing waves. So the first statement is that particles between adjacent nodes oscillate with varying amplitudes. Well, we can have a look at the diagram below. We can see the amplitudes there vary between node, antinode to node again. The particles between adjacent nodes are moving in phase with each other. Well, all of these points are at the bottom of their journey, if you like, their trajectory, whilst all these points are at the top. So these points are all in phase. So we're happy with 1. Part A, and we're happy with B. The particles immediately either side of node are moving in opposite directions. Well, that must also be true. These particles have just travelled up to get there, these particles have just travelled down to get there, so we're happy. again with C. The particles undergo node disturbance at an antinode. Well, that one is wrong. Antinodes, remember, are maximum displacement, so we're going to say D. Question 2, we're told that we've got some apparatus set up, which includes a vibration generator at 60 Hz, and it produces a standing wave. So you've done this experiment, this is Meldey's experiment essentially, and we need to work out the wavelength of the standing wave. Well, the wavelength is 2 loops, if you like, so that's 2/3 of 1.5 meters, so that's a nice, easy, straightforward answer of 1 meter. The frequency of the vibrator is altered until standing wave has 2 more nodes, so that's going to be 5 nodes in total. We need to calculate the new frequency, so we're going to have to work out a new wavelength to work out a new frequency. What we need to know first, though, is the speed of the wave. So we could do wave speed is frequency times wavelength, and that means that we've got a wave speed of 60 meters per second, and that's going to be the same in the string no matter how many nodes or antinodes that we have. That's set solely by the tension and the mass per unit length of the string, if you remember. So then it's just a case of rearranging to find our new frequency. So frequency is V divided by lambda. Our new wavelength would be there'll be 5 loops, which is the length of 2 loops, so 2 times 1.5 divided by 5, and then that gives us an answer of 60 divided by 0.6, or 100 Hz. So frequency of 100 Hz. The alternative way to work this out is, of course, to look at this and think 60 Hz is the third harmonic, so 60 divided by 3 would give us our fundamental frequency. 60 divided by 3 is 20 Hz, and then to find the fifth harmonic, then we're going to have 5 times 20, 100 Hz. For question 3, we've got 2 students demonstrating standing waves to the class using a rope or a slinky, and they've managed to get this so it's vibrating at 3 times the fundamental frequency. And we need to mark the position of nodes on our diagram. So if it's a string, vibrating string, we know that there has to be nodes at either end, so a node there and a node there, and then because it's the third harmonic, there must also be nodes between these antinodes, so a node there and a node there. So any of those positions works for you. For 1 mark, the arrow at point X shows the direction in which point X is about to move. Add arrows to the diagram to show the directions in which point Y and Z are going to move. So if X is moving down, then Y is going to be moving up, and if X is moving down, Z is going to be moving down. The frequency of the vibration in the diagram is 1.5 Hz. When a rope is vibrating with fundamental frequency, there's 1 antinode, so calculate the fundamental frequency. So this is nice and easy. If this is 3 times the fundamental frequency, all we need to do is 1.5 divided by 3. So very straightforward. 0.5 Hz is the fundamental frequency. Question 4 is not a difficult question, but I think it's not worded very well, and so it might have caught a few of you out. What we're told is that the diagrams show 3 things. At the top here we've got a stretched string. At the middle we've got a sinusoidal progressive wave travelling to the right along the string. So imagine someone's grabbed the string at this end here and just given it a flick with their wrist, and then the wave would travel towards the right. And then a stationary wave on the same string. So now we've got a fixed end here, and sort of oscillatory motion here, and so we're setting up a standing wave. And then we're told that P, so that's this line here, at a distance from X which can be varied. So P starts out at X, and then as we move towards Y, how do various things change? That's all this question is about. So how, if at all, does the amplitude of the oscillation at P vary as P moves from X to Y in the progressive wave? So we need to know what the term amplitude means. Amplitude, remember, means the maximum displacement. So you might be tempted to talk about the displacement, which decreases and then becomes negative. That's not what the question is asking for the progressive wave. It's asking for the amplitude. And the amplitude of the progressive wave, the maximum displacement, is going to stay constant at all positions along the wave, assuming that there's no attenuation effects. So the amplitude is going to remain constant. In the stationary wave, however, obviously the amplitude is going to be greatest at the antinode, decrease to the node, and then increase again. So it decreases and then increases. And then part B says, how at all does the phase difference between the oscillations at X and at P vary as P moves from X to Y? So we've done a little bit about phase. So what's the phase difference between point X and point P as P moves further away? So for the progressive wave, obviously it's in phase with point x at x, and then it becomes more and more out of phase, and it's almost at antiphase at y. Not quite, but nearly. So for the progressive wave, the phase difference increases. So in other words, P becomes progressively more out of phase with x as it moves from x to y. And then with the standing wave, the phase is a bit different. So all these points between the antinode and the node, in fact between the node, two adjacent nodes, are always in phase with each other, right? They're at the maximum displacement above the equilibrium point here. They're at their minimum displacement below their equilibrium point there. And then they'll move as one through equilibrium, below, through equilibrium again, and then up. So in terms of the stationary wave, what we've got are two things. As P moves from x to the node, P remains in phase with x, and then as it moves from the node to y, then it's in antiphase with x. So these points are all in phase, these points are all in antiphase, the next points would all be in phase again, these would be in antiphase again. Question 5, we've got a steel guitar string supported between two supports. So obviously this is a stringed instrument, or a string, and then we're told the length between the string, the length of the string between the supports is 0.65 meters. So state the wavelength of the standing wave. We've got one antinode between two nodes, so half a wavelength. So it's simply 2 times 0.65 is 1.30 meters. We're told that the fundamental standing wave produces a note of frequency 280 Hz. Calculate the speed of the waves. So we've got a wavelength, we've got a frequency, that means we can work out a wave speed. So V equals F lambda, stick in our numbers, 280 times 1.3 gives us 364 meters per second. And then we're told that we can work out the fundamental frequency of a standing wave given by F equals 1 over 2L times by root T over mu. So this is just our Meldey's equation for the wave speed. V equals root T over mu, where V is F times lambda. Lambda is 2L. So if we're going to do root T over mu divided by 2L, that's the same as doing 1 over 2L times by root T over mu. We're told the tension in the guitar string shown in the figure is doubled. We need to calculate the frequency of the new note. We can assume that everything else remains constant. So, question is, what happens to the frequency if this value T is doubled? If we're going to keep everything else the same, so the length of the string, mu the same, then we can say that F is proportional to root T. And so F is equal to the fundamental frequency, F0, times by root 2. And so all we need to do is multiply our fundamental frequency by root 2, which is about 1.41, and we get 396 Hz. If you think about what would happen in reality, however, the mass per unit length wouldn't stay the same. As you're stretching something, it has to get thinner. It's kind of conservation of matter, isn't it? If it gets longer, that extra length has to have come from somewhere, and that comes from the decrease in the diameter of the string. And so we need to state and explain the effect this would have on the frequency, because what we're doing when we're stretching that string, making it thinner, is decreasing the mass per unit length. And so going back to our equation here, we're going to make mu smaller. And again, we can say that the thin string means a lower mass per unit length, and so F is proportional to root 1 over mu, or 1 over root mu, same thing. And so as mu decreases, the frequency will increase, and so F would actually be greater than 396 Hz, the value we've just worked out. In part C, we're told that by placing a finger lightly at a certain place along the string, it's possible to produce standing wave patterns of different frequencies. We need to sketch on the figure one of those patterns. So we're going to keep our nodes at either end, and all we're going to do is just sketch on very quickly. Most of you have probably done the first overtone. You could have done second, third. So like those diagrams back on page 2. All we have to do then is calculate the frequency of the note produced by the standing wave we sketched, and we're assuming our frequency of the fundamental is still 280 Hz. So if you've done the diagram like me, which is just the next harmonic up, we've halved our wavelength, and so we're going to get double the frequency. So in the case of the one that I've drawn, we're just going to do 2 times 280. If you've done 3 loops, it's going to be 3 times 280, 4 loops, 4 times 280, etc., etc. My answer is 560 Hz. You need to make sure that your answer is consistent with the diagram that you've drawn. For question 6, we've got standing waves in air, and we've got an open pipe instrument. So this is going back again to the diagram on page 2. And we're told that we've got a pipe which is 2 meters long, open at both ends, so we're going to have an antinode at either end, and standing waves are produced in the pipe. We need to draw a sketch of the fundamental standing wave in this narrow pipe, so we've done that earlier on in the paper. So antinode at either end, node in the middle, something like that, and then we're going to do that. So one of those crosses. We need to take the wavelength of the fundamental node used by the pipe. Well, if the pipe is 2 meters long, we've got here antinode to antinode is half a wave, and so it's simply 2 times 2, which most of us will work out is 4 meters. For the rest of this question, we're asked to consider the effect of a variation in temperature. Change in temperature changes the speed of sound in air, so that's going to change the frequency of the note produced in order to maintain the same wavelength in our pipe. So we're told the speed of sound in the air depends on temperature, and the equation for that is that the speed of sound in the air is V0, which is 331 meters per second, plus k times theta, where k is 0.61 meters per second per degree Celsius. So what that means is that at 0 degrees C, freezing point, then the wave speed is 331 meters per second. For every degree C hotter than freezing, the wave speed increases by 0.61 meters per second. And we're asked to work out the speed of the sound in the pipe when it's 10 degrees C ambient temperature. So we've got our equation, V equals V0 plus K theta. So 331 plus 0.61 times 10 gives us an answer of 337.1 meters per second. We're then asked to calculate the frequency of the fundamental note produced by the pipe at 10 degrees C. We've worked out the wavelength earlier. We know the wave speed. We can work out the frequency. So V equals F lambda, our really important wave equation, gives us rearranged to F equals V over lambda, and then stick in our numbers. So 337.1 divided by 4 gives us 84.3 hertz. In part B, we're told that the air inside the pipe is heated and the frequency of the fundamental note produced by the pipe is found to have increased by 5%. So we need to work out the new fundamental frequency first of all, so that's just 84.3 times 1.05, and that gives us 88.5 hertz. And then calculate the temperature of the air in the pipe. We go back to our equation and it's just a matter of rearranging. So V equals F lambda, we've got a new frequency, so we're going to be able to find a new wave speed. So the wavelength, remember, is just the length of the pipe, it's fixed, 4 meters. So 88.5 times 4 gives us a wave speed of 354 meters per second, and then we can just plug that into our equation. So V equals V0 plus K theta. We need to find the temperature, theta. We know the wave speed that it used to be. We know the new wave speed when the fundamental frequency is increased, and we've got a value for K, our constant, of 0.61. And so if we rearrange this equation, theta equals V minus V0 over K, it's just a matter now of plugging in our numbers. So 354 minus 331 divided by 0.61 gives us a temperature of 37.7 degrees C. Question 7 is about the formation of standing waves in the microwave oven, and what they've done here is they've put a plate of marshmallows out, having removed the turntable from the microwave oven, put a plate of marshmallows in, and then allowed parts of it to melt and parts of it to remain unmelted, as the parts of it are under antinodes and parts of it are under nodes. We need to work out the wavelength of the microwaves first of all. We're told that the frequency of the microwaves is 2.5 gigahertz, and what we need to do there is just go back to our equation, which is that V equals F lambda. Here I'm not using V, I'm using C, because microwaves, part of the electromagnetic spectrum, travel at the speed of light, and we give that a C, the symbol C in physics. So C equals F lambda, rearrange lambda equals C over F, and that gives me 3 times 10 to the 8 divided by 2.5 times 10 to the 9, 0.12 meters. And then we're told that these marshmallows don't melt uniformly. The melting is concentrated, regularly spaced spots 60 millimeters apart. It's been suggested these spots occur at antinodes of the standing wave set up in the oven. And we need to explain why the standing waves are set up. So we can say that waves are emitted from our microwave source, that the waves reflect off the side of the microwave oven, the emitted waves and the reflected waves superpose or interfere, and then antinodes form in positions of constructive interference, nodes form in positions of destructive interference. When you're explaining standing waves, this is a really good structure to have. Talk about a source, talk about a reflection, talk about superposition between the source and the emitted and reflected waves, and then talk about where you're going to expect to see nodes and where you're going to expect to see antinodes. If you learn that structure, you won't go too far wrong when you're explaining the formation of standing waves. For question 7 part C, we've got a representation of the variation in amplitude along the part of a standing wave within the microwave, and we need to mark on this the distance equal to one wavelength. So one wavelength is the distance between across two loops, so between three nodes or three antinodes if you like. So there's 1, 2, 3 nodes, so that distance there. And then we have to mark two positions where a multispot might be expected to form. We're expecting those multispots to form where the amplitude of the oscillation is greatest. So any of those antinodes can be labelled X and Y. And then for part D, we're asked to suggest and explain how the outcome might be different for marshmallows being melted with the rotating turntable put into the microwave oven. And what that means, if you're putting in that rotating turntable, is that the marshmallows are being moved through antinodes and nodes. So they're moving from hot spot to cold spot to hot spot, and that's going to give more even melting. Not even more melting, but more even melting. For question 8, we've got a tromba marina, an early stringed instrument. It makes it sound like a trumpet. And it's a single string stretched between two supports that can be made to vibrate with a bow. So kind of a very simple violin, I suppose. We first of all have to label the nodes and antinodes here, so this is relatively straightforward by this point hopefully. So we've got nodes at either end on our stringed instrument and an antinode in the middle. And then we're asked to use the principle of superposition to explain why the string vibrates to and fro with a large amplitude in the middle. So again, really what we've been asked is, why does a standing wave form on the string? So same old explanation. Wave is sent from the bow, travels down the string and reflects at the end. The initial and the reflected waves then superpose. Where the constructive superposition occurs at the centre, we get an antinode, so large amplitude oscillation, and then I suppose to finish it off, the destructive interference at each end causes the nodes. We're then told the length of the string is 1.9 meters. The frequency of the lowest possible note is 32 Hz. Write down the wavelength of the waves on the strings. So if it's node, antinode, node, that's half a wavelength, and that's 1.9 meters. So wavelength is 2.1.9 is 3.8 meters. We're then told that the frequency of the lowest note produced by the string is given by the equation f equals 1 over 2L times root T over mu. So again, that's our melodies equation, so wave speed, f lambda. So f equals v divided by lambda. So root T over mu divided by 2L is our lambda, or root T over mu times by 1 over 2L. Where L is the length of the string, T is the tension of the string, mu is the mass per meter length. Show the tension in the string is about 120 newtons. So we've got to rearrange this equation to give us T equals. It's a little bit ugly, and another problem we've got is that our value for mu is in the wrong units, so we need to sort that out. So the mass of 1 meter of string is 8 grams. We need to find out what that is in kilograms. So that's 8 times 10 to the minus 3 kilograms per meter. And then rearrange our equation. The really awkward thing here is the square root, so perhaps our best sort of starting point is to square both sides of our equation. So what we end up with then is f squared on the left hand side is equal to 1 over 2L, all squared, so 1 over 4L squared, times by T over mu. And now it's just a case of simply rearranging. So if we rearrange, we end up with T equals f squared times by mu times by 4 times by L squared, and then we just plug in our numbers. So 32 squared times 8 times 10 to the minus 3 times 4 times 1.9 squared gives us a value of 118 newtons as the tension in the string. We're then told that by touching the string lightly at different points, the player can produce notes of frequency 64 Hz, so double our fundamental, 96, 128 and higher notes. When the player light touches a point 1/3 of the way along the string, the note of 96 Hz is produced. So we need to draw a standing wave pattern seen on the string when this note is produced. So it's 3 times our fundamental frequency, so we're going to have, if you like, 3 loops as opposed to 2 loops. So something like, and again, excuse the really rubbish diagram, something that looks like that but probably neater. Now that's going to be produced when he basically places his finger on the string here. So he's changing the length of the string so that this bit oscillates, or I suppose that bit oscillates with the fundamental frequency. So he's put his finger 1/3 of the way down the string, changed the string length, and got 1 loop. This is important going on to the next, because the next question asks us why the player doesn't need to reach more than halfway down the string to produce any of the notes. And so what we can say with that is that by placing no finger on the string, the fundamental node of vibration occurs. By placing the finger halfway down, the string gives us our first overtone. We're going to get 2 loops or 2 antinodes formed. We're essentially halving the length of the string, I suppose. By placing the finger 1/3 of the way on the string, we get the second overtone, the third harmonic, if you like, the 3 antinodes, and so on and so forth. Hopefully that's relatively clear. For question 9, we've got experimental arrangements shown where we've got transmitting and receiving aerial for different types of waves, and we're told that waves travel to the receiver along 2 paths directly from the transmitter and by reflection. So we did this as a microwaves experiment. The waves arriving at the receiver are combined to give our resultant signal. So with the metal plate position A, the output signal from the receiver is at a maximum. Explain in terms of superposition how the maximum signal can be received. So again, this is how the standing waves form. So the transmitted wave and a reflected wave travelling in opposite directions superpose. At the receiving aerial, the waves meet in phase and so undergo constructive superposition, and so we get a maximum signal. The difference in this experiment to the one that we carried out, whereas we moved the position of our detector up and down the line to measure the distance between adjacent nodes, they're keeping the positions of the aerial and the detector constant, and then so the transmitter and the detector constant, and then they're moving the position of the plates. This is important on the next page. As on this page, we're told that the metal plate is moved away from the receiver to position B, causing the output signal to be a minimum, and again we have to explain why this is. So again, transmitted wave, reflected wave travel in opposite directions and superpose. By changing the plate position, we've changed our path length, and that's an important point here. And so what we need to say is the receiving aerial, at the receiving aerial, the waves are now in antiphase, and so they're superposing destructively, and so we get a minimum signal. For the third part of this question, we're asked to explain why the minimum signal won't necessarily be 0. You've got to think about this. What are the conditions needed for it to be 0? And if it's 0, what we need is the amplitude of the emitted wave and the amplitude of the reflected wave to be exactly the same. Now that's not very likely to happen at all. So for perfect cancellation, both the transmitted and reflected waves must be at the same amplitude. It's likely that we'll get attenuation of the waves, so that's a decrease in amplitude as we get further from the source. And so the amplitude of the transmitted wave will be greater than that of the reflected wave. The other thing we might do is lose amplitude on the reflection. Either way, if those 2 waves don't have the same amplitude, we're not going to get perfect cancellation, and so we're not going to get 0 amplitude. And for the last question, we're asked to calculate the distance between the positions A and B in the metal plate for radio waves of 830 centimeters wavelength. Make our reasoning clear. Now, let's think through this stage by stage logically. The extra distance travelled by a reflected wave needs to be half a wavelength, so that we go from constructive to destructive interference. However, if you think about what's happening when you've got that metal plate, the extra half wavelength path difference that you need needs to be made up by hitting the plate and coming back again as well. And so, because of that reflection, the distance from A to B is a quarter of a wavelength, so that the reflected wave, if you like, travels an extra half a wavelength. And so AB is a quarter of 30 centimetres, so 7.5 centimetres.